Where am I? So
This is a different setting.
Alexander.
that's Alexander on the left. You figure out who the guy is with the lampshade on his head? Yeah, this is the first faculty at the Institute of Advanced Study. So from left to right, Alexander, Morse, Einstein, Adela, Herman Weil, and Weber. And this is this is a picture of Fox. This was given to me by my friend Wilbur Whitman, who found out that I collected such things. It's signed in the upper corner by Fox. This was taken for some birthday party for Fox, and if you look in the collected papers of Milner, the 2 volumes, you'll see in the front of these photograph of Fox on it, and not Milner, but you'll notice that they actually photoshopped or did something to remove that guy in the background. It's the same photo, and then they took a piece of his jacket here and used it to get rid of the shoulder here and patch it over, and did a really bad job. But he gave Fox, some photographer who was there, took these for semi-professional photo, and Wilbur got a copy of this, and he went to Fox and he said, "Would you sign it?" I don't want to sign it. Come on, sign it. Fox took this little crappy ballpoint pen.
And Wilbur said,
You're a famous man, Ralph. You should sign it big.
Is there a good biography of Fox?
Is there a good what?
Biography.
A Fox? No. Every once in a while, Josef Chetinsky encourages a student to do a biography, and they try to dig up some stuff, but there isn't very much.
we had a student interview Wilbur Whitman, I think, over the phone, and Wilbur volunteered that he'd never been in jail.
Never been in
Came
jail.
out in the biography. Wilbur Whitman has never been in jail.
So I kind of tried to squeeze some information out of Murasugi out of Fox, and the best he would tell me is that Fox really couldn't speak Japanese. That's complete rubbish, and his Go playing wasn't very good. And there's these stories that he went to Japan to play Go. And it's just nonsense. Okay, so I'd like to finish up this series of talks that Susan and I have been giving in the past 2 weeks, and do a couple of things. I want to specifically show you how homology with finite permutation representation, such as one some of you have been computing with, can actually be seen as an ordinary homology of something. So this is one case where twisted homology has a nice visualizable description. It's not particularly new. It comes from some fairly standard results in algebraic topology, but I'm going to try to present it in a way that makes it look a little more motivated without trying to be completely rigorous. So, and I'll tell you how you can make it, how you can check everything. So, hopefully only the mistakes will be new. So here's our setup. We have a representation from a knot group to GLNR. R as always is a Pythagorean UFD. And we've been using lambda as a notation for the Laurent-Paul regular. We've got this very intimidating chain complex, which has lambda in it, has V, that's D. V is R to the n, with a standard basis, E1 for En. And pi acts on that. And then we have the chains on the universal cover. X tilde recalls the universal cover. So yeah, what are they over? This is over Z pi. Yeah. And this is just over this is just over lambda. The way to think about this What is it?
It's over R.
So what
R.
overall? This is over R. This is over. Yeah, maybe I should put that in. R. This is over pi, and this is over R. Okay, that's fine. Thanks. I like to think about it this way. These are just coefficients. Just think about them as coefficients. For every chain down below in the base space X, we choose a fixed lift in universal cover. And then we think of this as we can act on any of those chains by an element of the group, and it moves you around universal cover. But that element that you're multiplying by can also come over here. When it comes over here, its action is to, the group will act on V the way it does through the representation. And it will also multiply the polynomial ring by T raised to the augmentation of that element. I'll show you again and remind you how this goes. But it's really not that bad. Now you've got a whole homology theory here. So there's a first homology that we're most interested in. And there's many notations for this. And like I said, Livingston Kirk introduced one that's we've been using this for. Pick one, but there's others. I'll try to suggest another one soon. So this is the first homology. And if we look at the zeroth characteristic polynomial, this is gotten the following way. You take a matrix that represents this module. You take a matrix that represents this module over lambda. And then you look at all the maximal square submatrices. You take the determinants, take the GCD. That's this thing. And this thing is sometimes called the twisted Alexander polynomial. It's one of the things that competes with Wada polynomial, the Wada invariant. And some of you have been computing a Wada invariant. That's much easier. The difference usually insignificant. So on the other hand, we have this other module that Susan talked about and I talked about a little bit, and it will come up again. And this module, we call it the based twisted Alexander module, is relatively easy to compute. And its zero characteristic polynomial is the Wada invariant. Okay. So let me show you.
Numerator is a lot.
Yes, indeed. Thank you very much. Yeah, it's the numerator.
So
Yeah, called the Lin polynomial. Thank you. It's the Lin polynomial. Always correct your notes as you correct. All right, so let's write down some chains. Generally there'll be no three chains if you've got a knot or a link complex because you can crush them out. We're not going to worry about it. We have a boundary operator, and we have another boundary operator. Now, to zero. Now, if we started with a standard complex, a zero cell, one cell, two chains, and then so over here, all we would have would be all we need for generators is one V, where V ranges over the standard basis, tensor our single zero cell down in our base space. So here V is always going to be assumed to be in the standard basis. So this is the basis for this thing. And let's write it backward. This is the module generator. Okay? This is all these are lambda modules. I don't need anything but one here because I can use polynomials to multiply what I want here. And if I just have V ranging through here, then I don't need other things in V.
What if we took the multiplication away?
Yeah.
Do that later.
Yeah. You take the augmentation lambda. Yeah, I know what you're thinking.
Yeah.
Things are a little less nice than they are in the classical case. Now over here, I want to do something. I want to consider the one chain, one V tensor x0. Remember, x0 is our designated meridian that we're basing. And then we got the other ones. So we're going to have a direct sum. And I'm just going to write one tensor V tensor xi, the others. I equals 1 to n. So this is here. This is here. This is a useful splitting. And if you think about the boundary map, it'll send these over by, let's call that map D0, because it's acting on the 0 chain. And then the rest. So plus, it's called D1. This is as bad as the notation will get. If you really want to give names to these things, you can. But my goal is to just get one particular result, which is very nice and very useful. Okay. So let's look at what happens when we take D0 and we map here. Yeah. Well, you know how that goes. D0 is going to send this chain 1 tensor B tensor X star to T Vx0, the matrix tensor star, minus 1 tensor V tensor star. We're talking about that. And because T times X0 minus the identity is obviously because this thing isn't 0, this map D0 is 1. Now, suppose you're looking for cycles. This is why computing this thing is very difficult, generally. If you want to find cycles, you've got to look at all the things that vanish here. Generally, it gets very messy, especially when you're working over Z, ZTT inverse. It's very hard to find these, generally. But notice that because all these things go 1 to 1, it's not too difficult to see then that your cycles are isomorphic with something in here. In fact, it's sort of like everything here goes over here with a unique tag from here, and then whatever this image is. And so just think about this stuff going over. So if we want, we can say that the cycles, Z1, can be regarded as inside here. Like I said, they're isomorphic to a submodule inside of here. The other stuff. This is where it might be nice to have a name for this other stuff. So, what we could do is just look at these things, and if we look at the kernel of D1, inside we'll have the stuff that's isomorphic to our cycles. We could also look at the image. We could look at the image of what's coming in under del 2. But of course, we have to project. We have to project onto this stuff. So let me just say project, because you got to project onto this factor coming over. You may have some stuff in here. And when you do that, this thing is this thing will contain inside of it as a submodule H1. When I say H1, I'm just being lazy. And what I mean by H1 is always going to be this twisted stuff. So that's inside here. What is it exactly? It's the submodule consisting of the cycles modulo this stuff. But if we just take all of these things and regard them as cycles, that's exactly the cycles that we need for this module. This module is precisely regard these things as cycles, and just look at the co-kernel of the boundary operator. That's what some of you have been computing. When you take this big matrix, you ignore the column corresponding to X0, just look at the others, and you look at the boundaries coming in by box calculus. That's what you're doing. So what I'm saying is that this is that module. Now, what's the good of this? First of all, it tells us that this homology is inside of it. And then automatically tells us that in fact, that's one quick way of seeing why delta 1 in fact will divide D1, D gamma. Okay. But in fact, even more, if D gamma is non-zero, that's the delta zero module, that's the zero characteristic polynomial on that, then this module is torsion. This is standard lambda module. It'll be annihilated by D. Hence, so is H1, because H1 is inside. And also notice that D gamma is non-zero if and only if delta 1 is non-zero. It's not difficult to see what that's. So.
Delta 1 or
Delta
delta 1?
1. The delta 0 is delta 0. Okay, now here's another really nice thing about this module. As you've already discovered, it's got a square presentation matrix. Right? You've been writing it down. This is a square presentation matrix. Now there's a nice lemma of John Hillman. We really didn't know about this until recently. I wish we'd known about it sooner. We found things a little bit harder than we had to. But this lemma says, let's let, here I just want to take lambda equal to ZTT inverse. I'm not sure, I don't remember to what degree it's general in his book, but so this is in his most recent book on invariance of knots and lengths. But it's certainly true for ZTT inverse, so let's just do that. A finitely generated torsion, oops, that's a G. Finitely generated torsion lambda module has a square presentation. If and only if it has no non-zero finite submodule. No. That just means it has no Z torsion. So one of the consequences, this thing has a square matrix. If its annihilator is non-zero, it's sorry, how to say this again? Yeah, if D is non-zero, then this is torsion. So it's a finitely generated torsion module with a square matrix presentation. Therefore, this thing has no non-zero finite submodule. Therefore, this thing has no finite non-zero submodule. Therefore, this thing is finitely generated torsion with a square matrix presentation. And so we get as a corollary something very useful. If D1 is non-zero, and yes, D1 can be zero, but if D1 is non-zero,
D gamma?
D gamma, thank you, then H1 has a square presentation matrix. And moreover, and if you multiply delta 1 times H1, you get 0. In other words, it annihilates. Whatever this polynomial is, it'll wipe out everything. There's other ways to see this, but this might be the fastest.
I'm sorry, delta 1 is your delta gamma here.
Oh, okay. Delta 1 is my. Yeah. Okay, feel free to tell me that stuff.
Right.
Thank you very much. Okay, so now this is preparation for the result of film I want to show you today. So let me do one more thing, and then we'll really have the preparation in place. Suppose gamma goes from pi not group to, this is a symmetric group on n symbols. And I want to assume that whenever I write a symmetric group, I'm always going to think about it as being inside GL capital NZ as permutation matrices. So this, in other words, this permutations here can be thought of as permutations on E1 and En by these matrices. These are the permutation matrices that have only a single 1 and zeros elsewhere in each row of column. So let's assume that this is a finite permutation, finite image permutation. It's random. Let's take a specific example. I is xy, xyx is yxy. This is trefoil, everybody's favorite con, everybody's favorite presentation. And let's take a gamma, setting little x to big X, which I'm just going to choose to be this. Think of this as coming from Fox coloring, because this is a symmetry of an equilateral triangle, holding the first vertex fixed, flipping the other two. And let's take a y, would be, in fact, you could just take any other element of the dihedral group. I'm going to take that. Okay. The single one is the vertex of the triangle that's fixed. And let's down here take x and y and a base point. This is a picture of x. It's a well, it's a complement. It's x is homotopy equivalent to this picture of x. And then we can take a universal abelian cover. Now, how am I going to think about this? This is the universal abelian cover. I'm going to write this chain covering here as one tensor x. Forget about v. There's no v. One tensor x. I'm going to think about this one as t tensor x. Up here, I'm going to have one tensor y and t tensor y. Now, of course, there's a relation given by this. And when we lift that relation up here, we're going to get a whole sequence of relations. They're all going to be equilibrium. Okay, but now I want to build another thing. I want to take this vertex and I want to split it into 3. I'm going to call it 1, 2, 3, corresponding to the set A. And now I'm going to lift this. It's going to start at any one of these points, but the vertex it ends up at will depend upon what the permutation big X does. If big X takes 1, 2, 1, as it does, then that tells me starting here I have to end here. If big X takes 1 to 2, 2 to 3, as it does, then I have to do this. This is a very standard thing to do. This is a cover induced by permutation. Okay. And I do it all the way across here. These are all my x arcs. And let's label this one 1 tensor E1. Why? Because that tells you where you start. Tensor x. And this one, for example, would be 1 tensor E3. Tensor V. So all this stuff is giving you location. This is telling you what sheet you're in, whether it's 1 or t squared or t inverse. This is telling you where you're starting from, E1, E2, or E3. And ooh, that's not a t, that's an x. And the x is telling you what you lifted. Okay, so now if we do the other ones, y is going to send 1 to 2. So y is going to do this. And then up here, we have these. And the same game with y. You label them in the same way. So for example, over here, let's say this one here, would be t, tensor E2, because that's where I started from, tensor y's. And then of course you lift your cells. It made you get a lot of cells. You get Rn lifted in 3 different locations. So let's write it this way. Rn lifting starting from here, or starting from here, or starting from here. And they're all going to come back into loops, guaranteed. They have to. All right, so I'm going to call this cover x hat. And now the claim is, you can really see it from this picture. I won't prove this, but at this point it's pretty well motivated, that the homology of x with twisted coefficients is isomorphic to the homology of that cover with ordinary z coefficients. So you are actually computing homology with ordinary coefficients of a finite cover of the infinite cyclic cover. It's a finite cover of the infinite cyclic cover. Now, the best way to make this precise is to use something called Shapiro's lemma that Susan alluded to. And that gives you a very general statement about collapsing coordinates. Basically, the idea is that, if you use coordinate z pi tensor, you'd be getting the homology of the universal cover. If you were to collapse this by the commutator subgroup, then this is just z. Think of this is the powers of t. And now what's happened is you've essentially collapsed all your cells. You're looking at the homology of the infinite cyclic cover. And you can see why that is. I won't go into the details, but that's basically what Shapiro's lemma is about. Is about collapsing this thing in which you can. So in particular, you can go further. You collapse z to z mod r. If you collapse z to z mod r, imagine here you're just coming back to where you started after r spots, after r times. Or over here you're coming back after r times. So if you fold this, collapse by t to the r equals 1, then you'll get the r-fold cyclic cover that Susan was talking about. And here, if you collapse it, you'll get a cover which we're going to call the r-fold cyclic. Just imagine coming back to where you started after r times. So you get a twisted homology of the r-fold cyclic cover if you took your coefficients t to the r equals 1. Again, this is stuff that we can get from Shapiro's lemma. Now, if you fill in the meridians, these are only the one complexes. You should imagine 3 manifolds. If you fill in the meridians, you'll get the r-fold cyclic branched cover, as we talked about last time. And above that, there's a cover, just as there is from here to here. Now this one's a little more complicated than this. This is the fundamental group of this is the fundamental group of this. It's the fundamental group of what you'd be looking at if you close this up. But then modulo some bits of meridian powers which have to kill. So the fundamental group of this is a quotient of the fundamental group of this. It's a little more complicated, but that's all we need to know about it. One other thing, you can guarantee that you've got a regular cover in this game if you do certain things. You can't always assume you're going to get a regular cover, but if well, I'll say some more about that when we go to it. Let's just go on and hit the main theorem. Yeah.
So the boundary map on the x hat is just to the boundary on the x.
The boundary hat on x hat is exactly the boundary operator that we've been computing. It's exactly the same thing. For example, the boundary of this chain is T tensor E3 hit by X star minus 1 tensor E tensor star. In other words, it's that base point minus that base point. Okay? That's how it works. Just like it.
In that model, how are you getting the action of the matrices sort of moved into
The matrices are telling you when you lift the cell, they're telling you where you wind up. The matrices are permuting E1 through En. So when I lift this cell, wherever I start, say 2, I'm going to wind up wherever the matrix X sends E2. I'm going to end up at the vertex corresponding.
If you took some, like, brought in the XY, then it would be sort of 2 maps, is that?
What do you mean XY? A product of 2.
I mean,
You can't can't really think of it like that.
So the notation's a little bit weird, right? Because x and x prime don't depend on your representation.
These two,
Right,
yes.
but x hat depends
Oh,
on your
yes, yes,
representation
yes, yes.
of the space itself.
And I'll tell you what's
Yeah.
going on. What's going on here is we're really looking at the representation restricted to pi prime. You can do this whenever you've got a representation on pi prime. You can go to a cover. Because this representation actually came from a representation on pi, which meant that there was a place for the meridian to go, and therefore the meridian went to something of order, some finite order. This cover has a nice kind of a periodicity. That's what you're saying. But what you're asking is how come you don't see the action here? It's because this is really all about the cover of the infinite cyclic cover. And it's really about that, folks. The fact that we can extend this representation over pi is good news, because it means that we're going to have actually finally generated homology. That's the catch. And it's interesting to think about covers you get from representations here that don't extend, that are sort of always, they're never periodic. And those will give you homology modules that aren't flatly generated as T inverse models. But yeah, so that, I hope that answers the question. It's a little strange. It looks like, where's the representation? I'm kicking in to get to the top. That's right. It's because this is really, from this point of view, it's about representations on pi prime.
Can I ask my question?
Sure.
Before we were doing computations like one tensor, E3, XY, tensor.
Oh, yeah, I know what you're saying. Oh, yeah, I know what you're
Can you
asking.
view those as maps in that space?
You should view it
Is that
as,
the-
you should view it like this. This is just, remember, these are permutation matrices. This is just going to be some EI. Is my,
Oh, so the finished product.
I know what you're worrying about. You're worrying about, you're
finished
thinking you're going to get a combination of E1 minus E2.
I was just thinking you would get T's by sort of.
Oh, no, okay,
forward.
yeah. The T's are taken into account by which sheet you're in.
So the XY is
And-
just tells you in one vertical line. Where
Yeah, and remember that we always have this action. This is, remember I wrote this down before. You always, that's how T acts. It shifts you on. That's right.
X hat is just the covering corresponding to the kernel of the representation.
No, you got to be a little bit careful here. The fundamental group of this is the stabilizer of your favorite symbol. But it is the kernel of a representation if you do this correctly. So I'll come to that. Not quite so simple. The fundamental group here is the stabilizer of a symbol. It's the stabilizer. This thing, pi acts on 1 through n. And if you look at what stabilizes 1, that's the fundamental group. So it's not necessarily normal, but it will be if we choose our set. That's a good question. Okay, so anyway, with all that preparation, now I think at least this argument can be motivated. So here's the theorem. If K is non-trivial, then there exists a finite image permutation rep gamma from pi to GLNZ for some n, such that the twisted polynomial is not invisible. Let's try to give a reason for this. Well, the first thing, you've already noticed that if you have the standard, just the trivial representation, 1-by-1 matrices of 1, you're going to get the ordinary Alexander polynomial back. So since delta gamma is delta for trivial rep, gamma pi 2, let's write it out, GL1C, taking xi to to the matrix 1. This whole thing immediately reduces. The problem is about Alexander polynomial 1 plus. So considering knobs. Okay. Delta. When I write delta with no gamma, I use the classical algorithm. Okay, so what does that mean? Equivalently, this means that the first homology of the infinite cyclic cover is true. Now, Susan mentioned the homology of the R-fold cyclic branch cover again by filling in, completing the unbranched cover by collapsing those two entries down to copies of the knot. That the homology here is simply the homology of the infinite cyclic cover modulo TR minus 1 acting on. This is a very standard fact. If this is trivial, then that's trivial. So therefore, H1 of MR is 0 for all R. Excuse me, triple?
It's not XR, that's...
TDR.
Okay. Okay.
Yeah. Okay. So that's that. But there's a 3-manifold, closed 3-manifold. So therefore, MR is a homology 3-sphere for all R. It's by quantum duality. All right, we need 2 ingredients to cook. First ingredient is a theorem of Lackenby, which really generalized a lot of results by many different people, including Reed and Iglo and Cooper and Long. And the final upshot was the following very beautiful result which appeared a few years ago. If K is a non-trivial knot, and L is an integer bigger than 2, then for all sufficiently large multiples, M, I'm going to take M times L, pi 1 branch cover order Lm has a non-abelian quotient. In other words, you can find a homomorphism onto a free group of rank 2. That's good enough to get any. That's good enough, but non-abelian. In particular, large enough branch cyclic covers have large fundamental groups. And large here means they have quotients onto non-abelian groups. Several proofs are given in this paper on archive. I'm not sure, I forgot where it appeared finally. Several proofs are given. Some of it's very proof theoretic. Some of it's topological, and some of it uses the orbifold theorem, and there's all kinds of ingredients that go into this. So what we really have to consider was satellite knots, and hyperbolic knots, and all the different cases, and torus knots. And then using lots of results by other people and putting them together with some new ideas. This is what comes. The other ingredient we need.
I have a question about this. Is the notation an accident? Are you using L and M that?
I'm trying to pick letters that haven't been used.
I mean,
There won't be. We won't have to worry about
Longitude and meridian.
No. I just was trying to think of any available letter, and we won't need it at all. So at some point, I'm just going to say there's an R big enough so that we have a big quotient.
Okay.
Oh, I just want to give you the full statement.
Is there any bound on sufficiently large? Or
Sufficiently large multiple. Sufficiently large.
is there any
multipliers.
upper bound on what you,
I don't think
in
so.
terms of the knot?
These questions, how far you need to go, are really tough. In fact, there's lots of questions of that nature surrounding this subject. Yeah.
Why not just say pi 1 of MR has non-abelian
Well, that's fine for us, but I'm just trying to be fair to Academy and state the theorem as he proved it. We only need the fact that there's one. Okay. One big enough. Or big enough. Okay. So the other result is a theorem of Milner. Well, it's kind of what eventually came from Milner's statement. But the theorem is that the only non-trivial perfect group that acts freely, that can act freely on a homology sphere is the, sometimes written A5 star, the binary Hausdorff group. Of order 120. And I remind you that perfect means commutator subgroup is the group. This condition, that the homology of the infinite cyclic cover is 0, is equivalent to the condition that pi prime is perfect. We'll come back to that. It's the same thing. And so here's the proof, modulo, just one combinatorial group theoretic lemma, which we can talk about at this time, but I won't. So, but at least show you how the pieces come together. So for some index R, there exists an epimorphism from pi 1 of MR to a group sigma, where sigma has size n bigger than 120. And remember, this is the group of we're considering an arbitrary Alexander polynomial 1 now. That's some pi. But now we're looking at some R-fold cyclic branch cover maps onto some big group. Because look, if you can map onto a free group of rank 2, you can get arbitrarily large quotients of free groups, of non-abelian free groups. So it's very easy to do that. Once you've got Lacani's result, you get very large quotients. All right, so we want to pull back to a rep. I'm going to call it G because gamma is not quite distant. So let's say G from pi prime to pi MR to sigma. And I'm going to remind you that pi 1 of MR is pi prime, just like the first homology is the quotient of the homology of the infinite cyclic cover. The fundamental group is a quotient of the fundamental group of the infinite cyclic cover. And what you have to mod out by is the meridian to the R, A, meridian minus R is A for all A in pi prime. This is a standard result. It's one way to think about the fundamental group of the R-fold cyclic cover. Get this CR action. Now here's the technical lemma that's not difficult to prove, but it just, you have to mess with some combinatorial group theory and some very standard ideas of semi-direct products. The lemma is that there exists a finite permutation, gamma now, from pi to, this is the symmetric group on n letters, and in fact, it's going to be the symmetric group on these elements. And the representation is going to be given by right regular representation. I don't want to go into this detail. Let me just tell you what the statement is. This is thought of as inside of GLNZ, such that gamma restricted to pi prime is R periodic. Give me a moment, I'll remind you what that means. Susan mentioned it, transitive. And furthermore, the size of the image of the commutator subgroup is n. So we call gamma restricted to pi prime is R periodic if gamma x to the R x to the minus R is gamma A. So you see what's up here. We're trying to factor through the fundamental derivative of the R full cyclic cover. R full cyclic branch. This should be true for all of them.
Yes, I think I was always dealing with the abelian version, you
Oh.
know, t to the R times A, but
Okay,
this
yeah.
is the non-abelian.
This is the non-abelian version of what Susan was writing there. And when she was writing T acting on or something, that was the same thing as, yeah, it's actually multiplication by T is conjugation X inverse R A X R, but it's the same thing. A inverse. That's right. Okay, so also, let's see what do I need to say. Gamma restricted to pi prime is transitive. Well, it means if for all I and j between 1 and n, there exists some element of the commutator subgroup such that EI times the matrix A is EJ. It moves you around. It moves fibers forward. And as I said, the way this works is you look at the symmetric group on this group, and when you've got an element in this group, it acts on the symmetric group by multiplication on each of the elements. This is just the Cayley representation of a group in a.
It's not really acting on this, it's just acting on the underlying set.
Yeah, it's acting on the underlying set. The thought of as symbols. The thought of as symbols.
Right, with it, and then you choose an ordering of that.
Yeah. But the nice thing about doing that is that then the stabilizer of an element really is a normal subgroup. And so that's good. The stabilizer of the element will actually be the kernel of this map. So you get regular covers. It's a good way to build covers. They're very large. And actually that's what we want. Okay, so now what's the point? What's the punchline? Well, you know, I've got a representation that's period R, but there might be a smaller R for which it's periodic. And we need to crunch down to the smallest R for which that representation is periodic. So let R be the least period. And we have to worry about a silly thing. Suppose R0 is 1. This would mess everything up. It cannot happen. And why? R0 is not 1 since we know that we're going to the symmetric group, but we could also factor through pi1 of whatever the period, the pi1 of m, whatever the period is. And if the period is 1, this is just the fundamental group of S3. This is the one-fold cyclic branch cover of the knot. Just means you take the knot complement, you put the knot value, you got S3. So this is nonsense because we've gone for a trivial representation. It would imply that this is trivial. So here's the idea. Consider M R0, the R0 fold cyclic branch cover, and then let's consider the induced cover of the representation. So this is induced, cover induced by gamma. So the group of covering transformations acts freely, transitively, on fibers. And we saw what a fiber looks like. Remember when we took a base point in the infinite cyclic cover and it became free? Well, here it's going to become capital M. So we're going to get the preimage of a fiber have cardinality n, which is bigger than 120. So the group of covering transformations can't possibly be the binary Laplacian. Since n5 star is order 120. Well, that means, therefore, MR0 is not a homology 3 square. Right on there. And if it's not a homology 3 sphere, then, well, let's kind of argue the by contradiction. If gamma, if the twisted Alexander polynomial, if this representation was 1, and from the things we said a moment ago, the homology of this cover would be 0. Remember that the ordinary homology of this cover is the twisted homology. It's the twisted homology with this representation. And because of the square matrix presentation, we know that this delta gamma annihilates it. So if 1 annihilates a module, that means the module is trivial. Okay, so that module is trivial, but you know there's always trouble when something starts with but H1 of MR0 12M is a quotient of H1XR because H1XR0, the untwisted cover, is a quotient. And then you take this, you mod out by TBR0 minus 1, and then you fill in the Brinell disks. You just keep adding stuff until you get your homology. So therefore H1 MR0 0, therefore MR0 is a homology sphere. That's not possible because it's shown it is a homology sphere. And so that's the argument. Therefore, it's not one for such a representation. The only thing I've left out is the proof of this lemma. And it's like I said, there's no topology in it. It's just a very straightforward argument with regular representations and just permutations and semi-hard polys. And I thought it would maybe be a little bit too much. You could read it in a paper on this subject. Have an archive a few years ago. So, and with that, I want to thank Alex. Thank you very much to you all for making this possible. And thank you all for attending the talks faithfully. It's a miracle.
Thanks. Are there any questions?
So if I understand the question that Aller was asking, this theorem tells us that twisted Alexander polynomials detect the unknot, but don't give an algorithm to determine if a knot that's sitting in front of you is or is not the unknot.
Yeah, I mean, look, let's be clear about one thing. As soon as you've got a representation to a non-trivial group, you've got a non-trivial knot. The interest, I think, with twisted homology isn't to get it non-trivial, as much as to see that the non-triviality of the representation is somehow preserved in all this machinery of homology.
Okay.
And I think that's really the issue. And so here's what Sis and I regard as maybe the most compelling open question. It's silly. Given a non-abelian representation, hey, make it finite, I don't care. A non-abelian representation, can the twisted invariance ever be true? I mean, you could say, well, give a faithful one, but hey, just non-abelian. And in other words, does the fact that you've got a non-abelian representation, which already tells you the non-proof isn't zero, does that somehow still survive in this machinery when you finally go through the chain complexes and you get the homology? So that's really what this is about. I don't think we're really looking for an algorithm to detect the unknown.
Okay, I understand now.
Yeah. It's, in fact, there's a ton suggested about maybe kind of misleading, perhaps. all these invariants, it seems like, I mean, again, it's just a personal attitude. I mean, I think detecting knots doesn't seem to be as much of a cottage industry as it once was. And with the plethora of invariants and things out there, the interest is to try to relate them, find out what they really say. The fact that it's so difficult to say what this quantity is for what Susan was calling a total rep of a parabolic total rep of a two-bridge knot. Although it turns out to be a relatively easy thing to write down. It's she said two dimensional representation. This is for total parabolic reps that Susan was describing. The fact that that's so hard to prove kind of suggests that we don't really have the best way of thinking about things yet. I don't know. I mean, this is so easy for untwisted model because it's telling you this. But it seems to be so hard for parabolic things. I guess there's a lot of picture in it.
Well, thanks Ben and Susan for 2 weeks of hard work.